Ladies and gentlemen, welcome to my webinar on Weibull plotting. And as you can see, for those veterans who have been in some of my previous webinars, we are now not beaming to you live, but you can actually see my face. Whether that, like I said, adds to the experience or detracts, well, subjective decision or subjective. Actually, let's roll with it being good. Anyway, so welcome to today's conversation about Weibull plotting. And we're not going to go too deep, and there's actually not going to be a single equation because a lot of the time when we talk about Weibull plotting and Weibull analysis, we tend to rush to the equations and then get overwhelmed with all that sort of good stuff. All these Euler's numbers this and betas that and etta's this, etc., etc., etc. And that actually means that we focus on sort of the theory more so than the signature. And because for those of you who don't know what Weibull analysis is, it's the preeminent form of life or reliability data analysis in the field of reliability engineering. And we're going to show you why that's the case today. I'm going to offer, for those of you who have dabbled with it in the past or haven't had any dabbling whatsoever, hopefully today we're going to take away some of the mystique of what Weibull analysis is. And if you're in any way, shape or form overwhelmed or perhaps intimidated by data analysis, let's try and do our level best to resolve that situation. Now, when it comes to Weibull analysis and reliability more broadly, the problem is that things like this ball bearing have the temerity to fail at different times. What I mean by that is that you can have, for example, seemingly identical ball bearings, and because failure is a random process, they will fail at different times, even when they're used in primarily the same way. Now, if my computer catches up for the next one, here we go. We're going to look at a number of ball bearings. Oh, my computer has decided to think about things. There we go. Number of different ball bearings. So seemingly identical ball bearings will have the temerity, like I said, to fail at different times. And that's okay. And the reason why it's okay is because it's a natural process. Even when they're being used in exactly the same way, in exactly the same plant, they're all from the same batch from the same manufacturer. One ball bearing, for example, on the left, it might have an impurity, while the one ball bearing on the right will have a dislocation at a particularly unique point in the inner or outer race. And it means that even if these ball bearings have been manufactured to the highest possible standards, there will be these invisible differences, which means that, amongst other things, we will have a different set of factors which influence how long each one of these ball bearings will last before it fails. And so because failure is a random process, we have to embrace that as reliability engineers. And that's not something we enjoy doing as technically minded people. The reason why we don't enjoy doing this is because the first thing we're taught when it comes to technical stuff and things like arithmetic is that 1 + 1 always equals 2. We don't have 1. So let's try and see what we can do in regard to capturing this omni-shambles with this random hand of failure, which is something that I know a lot of you who have been on my webinars in the past know what this represents. The random hand of failure represents all those different factors, all those impurities, defects, which exist in different places and different bearings, which then drive seemingly identical ball bearings to fail at different times. And then this line on the bottom, this axis, represents time to failure. Now, in the world of reliability engineering, we use the term time to failure a lot, but the word time actually represents perhaps the age of your system or how you measure how long damage accumulates for. So for ball bearings, this is going to represent cycles, a number of times the inner race rotates with respect to the outer race. And so if we test or observe a number of seemingly identical ball bearings, all those different factors I intimated at will cause them to fail at different times. And as an aside, one of the biggest factors which influences the life of a ball bearing is particle contamination. Now, all these different factors might seem like egregious faults or holes in the maintenance regime of whatever plant plant or whatever machine this ball bearing is located within. And sometimes that's the case. If you don't maintain your equipment, it will fail early. But the reality is everything has to fail one day. You can't avoid it. And eventually there will be particle contaminants, which, for example, in the case of our ball bearing, will accumulate in a way to contribute enough damage for your ball bearing to fail. You cannot escape these factors. You can control them, but even if in the best circumstances, we will eventually find that particle contaminants will eventually ruin the day of our ball bearing. And here is, I believe, 100 different data points. These blue dots represent, each one of these blue dots represents the time to failure of a single ball bearing. Now, just because something is random and failure is a random process doesn't mean it's not predictable. And you can start to see a little pattern, and you can sort of see that the data points are sort of collated in one region more than in another. But it's sort of hard to visualize this density. And so one really important tool that we use in reliability and statistics and other similar endeavors is the histogram. And here's a histogram for our times to failure for our ball bearing. The histogram does a pretty good job of visualizing the signature of our ball bearing failure. You can see that it sort of have a peak on the left-hand side. It's sort of skewed a bit. We've got the histogram tailing to the right. We call that a right tail, believe it or not. And so the histogram does a good job of visualizing that signature, which I was referring to. Now, if we were to test an incredible number of ball bearings, in a million, billion, trillion, quintillion, then our histogram would essentially disappear or collapse to a perfectly smooth curve like this. This is what we call, perhaps in some ways, the ultimate histogram. But for the more bookish people out there, the line on top of this curve or shape is called the probability density curve. And this curve essentially encodes the random process of failure for our ball bearing. This red curve tells us the relative likelihoods of our ball bearings failing at one time to failure value as opposed to another. The higher the curve, the more likely it is for our ball bearing to fail where that curve is the highest. And you can see that the curve clearly shows that there is sort of a peak on the left-hand side, skewed to the right with the right tail. So this is the signature of our random failure process for our ball bearing. Now, if you're with me so far, well done. Hopefully you haven't been too overwhelmed so far. And I'm not trying to be flippant or anything like that, because probability and statistics is inherently challenging for our minds to deal with. Our conscious minds like the arithmetic side of life. 1 + 1 = 2, not 1 + 1 is usually equal to something around 2 plus or minus a little bit. And our unconscious mind usually deals with all the randomness and the uncertainties. So for our unconscious mind, through practice and repetition, will learn how to throw a baseball or learn how to hit a tennis ball. There's lots of, our eyes will see a ball approach our tennis racket, for example, and it will do all the random data analysis behind the scenes. It will sort of tell the rest of our brain, our unconscious brain, especially been practicing, approximately how far away from our body that ball is, how hard we need to hit that ball, etc., etc., etc. And of course, it's not an exact science, which is why our unconscious brain is really good at it. The price we have to pay, though, for our unconscious brain to get good at processing all these random inputs is that it takes practice. We need to train our unconscious brain. Conscious brain is very different, doesn't like it. So just bear with me for a tick, because we're going to look at this probability density curve in a little more detail when it comes to that thing I talked about when I said signatures. So we have here a probability density curve for our ball bearing sitting on top of the reliability curve, which is now a brand new concept that I'm talking about. And why am I doing this? Because the probability density curve defines the reliability curve. Essentially, if we trace out the area under our probability density curve to the right of any point, like we're about to do right now, you can see that it traces out at this point in time our reliability curve down to 90%. So the reliability curve at that point in time is now 90% because the area under our probability density curve to the right of that point of time is 90% of the total area under the probability density curve. And as we move from left to right, you see that every single point in time has this corresponding relationship. At that point in time, our probability density curve and our reliability curve tell us that we expect about 90% of our ball bearings to still be working. And as we keep moving from left to right, or sorry, I got ahead of myself. This is what we call the B10 life for our ball bearing, the time by which we expect 10% of our ball bearings to fail. And we can keep tracing our reliability curve from left to right until it hits this point here where the reliability has dropped to 50%. This is the B50 life. Hopefully you can see where the B10 and the B50 life come from. That means there's a 50% chance that our ball bearings will still be working at that point in time. And it's also the point in time where there is 50% of the area beneath our probability density curve to the right of that point. I think I made a muddle of trying to explain that, but hopefully the illustrations do a much better job than my ham-fisted attempt to talk. And so as we keep going from left to right, you can see that it traces out this beautifully smooth reliability curve. So we have, for every probability density curve, a corresponding reliability curve. They encode exactly the same information, they just visualize it in a very different way. The probability density curve at the top is how our brains tend to like to visualize random processes, especially if a random value has likely to be around a central value and the less likely as it moves away. The reliability curve and the failure function curve, which is related to it at the bottom, is much better for us actually answering questions in a quantifiable way. It's a lot easier to measure the height of a curve than to measure the area under a curve, which is why the reliability curve is very helpful. So let's have a look at this probability density curve in a little bit more detail, because I can't talk about reliability without talking about this magical balance point there. Now this balance point, you can see that in this shape to the, is it to the left? Did you guys look? I'm not sure which, when I look ahead, what's being automatically mirrored or not. So that side of the screen, you'll see the probability density curve shape teetering on a perfectly central or perfectly balanced fulcrum. And you can see it's just teetering ever so slightly. Now that is the mean. The balance point is the mean. For any random variable, we often represent that with the Greek lowercase letter mu. You might know the thing called the mean time to failure. I've heard of it, I should say. And if this is going to be a component that's constantly replaced in a repairable system, then this could represent the mean time between failure. And then the mean time to, or the mean time between failure is often communicated as if it's synonymous or at least a measure of reliability. Unfortunately, it's not. And so if we have have a look at our probability density curve in greater detail for our ball bearing, we can see where the mean is at perfect balance point. And we can also see that, for example, this weirdly shaped curve over here, which is hugging the vertical axis in a way which doesn't align with our natural tendencies for visualizing random processes. Believe it or not, that curve, that orange shape, is also perfectly balanced at that balance point. And that is the probability density curve of the time to failure for small satellites. And that's because small satellites are inherently challenging to manufacture at high quality. They're not mass produced. They use sensitive components that are designed for other products like phones and computers and graphics cards and things like that. So small satellites are always launched into space with what we would, I suppose, what the manufacturing engineers amongst us would say is a lot of defects. And so you have a lot of these early failures, which is why you see this completely non-intuitive probability density curve for our small satellite. And when I say small satellite, we're talking about a really small satellite. But believe it or not, that probability density curve is perfectly balanced at that fulcrum. It's just that it extends so far to the right that it is the smaller area to the right of the balance point extends so far that it balances the larger area to the left, which only which is only just to the left of the balance point, so to speak. And so if I was to, for example, observe a huge number of small satellite times to failure and essentially put those data points on this line right here. Like I said, we know these things fail due to wearing or infant mortality, where a fraction of products carry those problems that cause early failure. So those that still work appear to be way more reliable, which is not, so the small satellites aren't magically getting reliable. It's just more like that the weaker ones are being weeded out. So what those that are left have on average, higher reliability performance characteristics. So this comes from manufacturing defects, assembly or installation error, interface issues, software bugs, damage during transit or launch. Lots of these issues that introduce pre-existing damage or problems will create this weird probability density curve like the one you can see on the screen right now, with a lot of this area to the left of the balance point. And if we look at our mean time to failure for our small satellite, you can see it is perfectly balanced at that point, even if you might not believe me. But now, if we look at the area under our probability density curve, like I said, a lot of the area is to the left. 80% of the total area on the probability density curve is to the left of that balance point. So 80% of small satellites fail by the mean time to failure. That's not the case for every system. For ball bearings, you'd expect about 54% of the old ball bearings to fail by the mean time to failure. So it's a lot closer to 50%, but it's not quite 50% because this probability density curve is not symmetrical. It's skewed to the right. And that's not the end of the story though, because there are some probability density curves which are perfectly symmetrical, like this bell curve. And you can see that for this bell curve, if this describes the time to failure of a product or system, and exactly 50% of those things will fail by the mean, which is exactly what we see for things like tires, where they wear out in a very uniform way. Now, why am I torturing you with this? And I know some of you veterans will to my webinars, I should say, will be aware of this spiel I give every single time. But what you've actually, number of different signatures of failure. These different shapes, these different probability density curves are signatures of how things fail. Now, for the last one we looked at, the bell curve, this is a signature of something that accumulates damage. And every time you see a probability density curve with a peak, you know that the underlying failure mechanism is all about the accumulation of damage, as is the case for the ball bearing as well. It's a different probability density curve shape, but it has a peak. And because it has a peak, we know straight away, without having to do any root cause analysis, the underlying failure mechanism is all about the accumulation of damage, or what we call wear out. Wear out can be caused by things like fatigue, oxidation, corrosion, creep, wear, lubricant contamination, diffusion. So these are some examples of failure mechanisms where essentially the older your thing gets, the more likely it is to fail, which is the exact opposite to that of the small satellite. And so when you have things that wear out, able to more easily, conceptually at least, process that random failure process. I use the word process twice in that sentence, shouldn't do that. Anyway, so these curves here are more the curves we like to see, our conscious brain likes to see, because they align with the way our conscious brain tends to like to process random processes. Here's it again. I'm saying process a lot. I'll try and stop that. Now, let's have a look at these curves in a little bit more detail. And hopefully the people who are saying, well, what you talked about the Weibull plotting. Why are we talking about that? We'll get to that in a minute. You can see that for this tire, we have essentially taken the total area under the bell curve, which describes the time to failure of the tire, and we found the area on the left-hand side, which accounts for 10% of the total area under the probability density curve. That is what we call the L10 life, exactly the same as a B10 life for a ball bearing. It's just that the ball bearing or bearing industry coined the statistic B10 life before anybody else. And the letter B represents or stands for bearing. And other industries and other engineers and other manufacturers said, you know what, I really like just something as simple as the B10 life to describe how long it takes for the first 10% of our things to fail. But we don't manufacture bearings or anything else that starts with the letter B. So the L10 life is used outside of the bearing industry for any product or system to describe the time by which at which we expect 10% of our things to have failed. And this is really important because the vital few failures are usually the first ones. Think about warranty periods. We can tolerate, as a rule, no more than 5 to 10% of our things, depending on industry, failing in our warranty period before we start losing, making no profit whatsoever. We talk about mission reliability. Usually they're the high 90%. So as a rule, we're not interested in the trivial thousands of failures. We are most interested in the first 1, 2, 3, 4, 5, maybe up to 10% of our things failing, perhaps no more. And so here is the L10 life that we can deduce from the probability density curve of the time to failure for our tire. Now, here is the L10 life for the ball bearing. You can see it actually moved to the left ever so slightly. Now, the mean time to failure hasn't changed. That balance point is the same for every single probability density curve we're looking at. So you can see that the L10 life for different products with different failure processes, even if they have the same means, will have very different reliability characteristics. And so now that we're looking at the bearing, we can now call that time to, or that statistic, the B10 life. You can still call it the L10 life. Maybe those in the bearing industry will look down on those who refer to the time by which we expect the first 10% of bearings to fail with the L10 life, not the B10 life. I don't know, but statistically, they mean the same thing. And you can see that's how far our L10 or B10 life moved to the left when our failure process changed from that for the rubber tire to that for the ball bearing. But it gets much more significant when we compare the L10 life for those two products to that for our small satellite. You can see the L10 life is so close to zero that you can't see the shattered area at all. So even things that have the same mean time to failure have very different reliability characteristics. Now, here's something that might blow some of your minds, and that is these three very different probability density curves, all these curves, and the bit that's about to blow your mind is not this bit, but it's they do have the same mean time to failure / mean time between failure if they're part of the a repairable system. However, these are all three examples or instances of this thing called the Weibull distribution. Even though they're very, very, very different, they are all generated by the same underlying equations. And there's a reason why that's really powerful and really useful. So the Weibull distribution is named after this guy here, Lotte Weibull. Come back here, Lotte. So Lotte Weibull, Swedish. He's gone. Sorry, let me see if I can keep him up here. Lotte Weibull was a Swedish scientist, and the reason why we use his distribution a lot. See if I can keep him up here for a little bit longer. Seems like I'm doing all right so far. Is that he was the guy who sort of came up with this this distribution. He wasn't the first guy to do it. That was a French guy who, as you know, a lot of really cool theories and really cool principles and rules and things like that aren't named after the person who first discovered them. But this guy is the first one to take this particular suite of distributions into, I suppose, the consciousness of reliability engineers. And there's a reason why. his distribution, or the distribution named after him, is so pervasive. And that is because it does a remarkable job of modeling real life failure mechanisms. Things like corrosion, things like fatigue, things like oxidation, things like dendritic growth. They are all natural processes that the Weibull distribution does a remarkably good job of modeling. And the reason being is the Weibull distribution is from a family of what we call extreme value distributions. And what does that mean? That means that they're based on the whole concept that if you get a bunch of different random variables, for example, get a bunch of them together, and then you routinely select the smallest one. So if you get, for example, 10 people, randomly select 10 people from, walking down the street. Oh my goodness. Let me get back there. If you randomly select 10 people walking down the street, and then you measure the height of the tallest person and the height of and then get another 10 people, then measure the height of the tallest person from that group of 10. You get another 10 people, measure the height of the tallest person from that group of 10. What you're essentially doing is sampling extreme values. And you can do the same for the smallest value. Get 10 people walking in the street, measure the height of the shortest person, get another 10 people, measure the height of the shortest person in that group, so on and so forth. And it's analogous to the sort of weakest link modeling, so to speak, in the natural world. And a lot of things tend to work onto the last remnant of strength in their microstructure gives way. And it just so happens that the Weibull distribution does a fantastic job of modeling all those different failure mechanisms because of that point. Essentially, as things wear out, they get to the point where they're down to the last remnants of strength. Sometimes the weakest part can be the thing that fails first, or sometimes it's the only thing left is the strongest part. And regardless of what scenario we're exploiting or mimicking with our failure mechanism, the Weibull distribution can do it. Not only that, the Weibull distribution can also model wear-in for the same reason, but in reverse. It's all about the weakest link being weeded out, so to speak. And because of that, if we can get a bunch of data and find the right Weibull distribution to model that failure mechanism, we can suck out a lot of really useful information. So here's our random hand of failure, for example, and we're going to look at one failure process, first failure process. And here it is there. So you can see that we have a bunch of blue dots representing the time to failure of a bunch of things that are blue in this case. And this so happens that these things are modeled by a Weibull distribution with the beta parameter of 3.5 and an eta parameter of 1.0. Those are the two parameters right there. So in my quest to make sure there's no equations in this discussion, I am going to have to go just a little bit into Greek lettering and everything else. Just understand that these two different parameters define a particular Weibull distribution, the bell curve you can see right there. So you can see that this thing wears out like tire tread wear because it has that beautifully symmetrical bell shape. Now we'll look at another random hand of failure for a different thing that fails. Now this red thing that fails, you can see the data points are scattered in a very different way. And this is based on a Weibull distribution with a beta parameter of 1.0 and an eta parameter of 0.6. And you can see you might think this is wearing in because it's sort of hugging the vertical axis, but it's not. It's actually anchored to the vertical axis. And what that means, because it doesn't have a peak and it's not going up or hugging the vertical axis, it's anchored to the vertical axis, is that this is neither wearing in nor wearing out. It has a constant hazard rate, which means if something has survived 100 years, it is just as likely to fail the next day as a brand new product or component. Now, this doesn't apply to too many things. In fact, Fred and I often try and brainstorm scenarios where this sort of failure signature can apply. And as a rule, the only thing we can really agree on is a coffee cup or a coffee mug or things that are terracotta things that you find in tombs to this day, which are thousands of years old. Essentially, the only way a coffee mug breaks is when you drop it. And it doesn't matter how old or young that coffee mug is, it's equally likely to be dropped by a human being on any given day if it's being used in a consistent way. So that's random hand of failure number 2. And here's random hand of failure number 3. And this green system has these data points we got from testing or observation. And it just so happens that this is data from a scenario just like our small satellite. We can see it has a beta parameter of 0.4. So this is the lowest beta parameter and an eta parameter of 6. And you can see how it's hugging the vertical axis. So this is clearly something that is wearing in, has tons of assembly areas or something like that. Now, one way of trying to see what's going on is to plot these data points on a chart where the vertical axis represents the percentage of things that haven't failed. One of the problems with the histogram is that it's very jaggedy until you get tons of data points. When you plot things like this, where you sort of accumulate the number of things occurring, the lines you get tend to be a lot smoother. So patterns start to emerge, but you're not going to see, for example, the bell shape, because that's going to only come out if you use a histogram. So those blue data points, you can see how they sort of create a line which has a very slow gradual gradient on the left and a steep gradient in the middle where the bell curve is the highest, and then it peters off on the right-hand side. So not intuitive in terms of the signature of the random process, but it is a smoother line. And we do like smoother lines when it comes to visualizing random processes because we're good at seeing smooth lines. And so what we're going to do now is magic. We're going to have this button here, this transform button. And this is essentially the heart and soul of Weibull analysis, where we press this button and all of a sudden these data points are plotted on a different chart. And this is a different chart because even though it still represents the percentage of things that have failed for each one of our three products, the green, red, and blue ones, there are some weird scales going on. Now, this is what we call Weibull probability plotting paper. And one of the things you should note straight away is that these data points are creating straight lines. Even though the green one is from something that was wearing in, the blue one was from something that was wearing out, and the red one was something that was not wearing in nor wearing out, like the coffee mug. So we know that a random process that is described by the Weibull distribution will create these straight lines if we plot these data points on this Weibull plotting paper. And so you see these 3 straight lines, which tells us that the Weibull distribution is almost certainly going to describe the failure process for each one of these 3 products, the green, blue, and red ones, even though they fail in very different ways. That is a really powerful thing to be able to do. So where does this magic straightness come from? Well, it has a few characteristics to this plot that make these data points, if you test them or get them from field data, create these beautifully straight lines if you know the underlying equations. Now, you don't need to know the underlying equations to create these charts because some people, really smart people, have already done this for us. And you might see that this chart is scaled in really weird ways to accommodate the underlying equations of the Weibull distribution. So all you need to do is plot your data on these charts and beautifully visible patterns start to emerge. One key thing is that you'll see up here, there is a blue line where the CDF, which represents the cumulative distribution function, i.e. the percentage of things that have failed, is 63.212%. So if you can see a blue line going straight across your Weibull plot, and it cuts through the 3 straight lines our data points create. Now, why is that there? Well, that is a really easy way of finding out one of those 2 parameters. Remember those random hands of failure with the beta and eta parameters? The eta parameter, the bottom one, is all about the scale, the sort of typical size of your random variables, or the typical time to failure. And if you cross that line, look at that, sorry, where that blue line crosses your data point straight lines and draw a line straight down, these give you immediate estimates of what that shape parameter should be, that eta value. So you don't have to use any equations to come up with a pretty good estimate of one of the two parameters of your Weibull distribution. But it gets better, because you can see that these three groups of data points, the red, blue, and green ones come from that thing that wears in, like a small satellite. Blue one comes from something failing with that beautiful blue bell curve, like a rubber tire. And those red data points comes from something that doesn't wear in or wear out, just like a coffee mug. And they all create these beautiful straight lines, and they all have their own gradients. And you can see the blue line is the one, or the blue data points creates the steepest line. The green data points creates the shallowest line. And the red data points, which is something that's not wearing in or wearing out, creates a gradient or slope, which is between the two. That gradient is the beta parameter. And so the beta parameter tells you if your thing is wearing in, wearing out, or neither. So whenever you have a slope, whenever the slope of your data points is quite steep, around about 3.5, the probability density curve it creates is a bell curve. When the slope is exactly equal to 1, it means that your thing is neither wearing in nor wearing out. So you have that red probability density curve, which is anchored on the vertical axis. And when the slope is really shallow, less than 1, typically it's between 0.3 and 0.5, your thing is experiencing wear in or infant mortality. And that is an incredibly powerful message, because you now know what you need to do to be able to go and improve the reliability of your product. So for example, if your product is experiencing lots of wear in or infant mortality failures, you're not going to look at redesigning per se to improve robustness. You might first look at manufacturing defects. Conversely, if you have a bell curve describing the times to failure of your system, if your thing's wearing out, then you're not going to be looking at the manufacturing process. You might be looking at the wrong bearing being selected, for example. And if your data points are creating a line which suggests it's neither wearing in nor wearing out, there's a good chance you stuff something up, because that rarely happens. Unless you're modeling the time to failure of a coffee mug, you rarely get the data points for an entire system failing due to a constant hazard rate. But if you do, it usually means that your product is failing due to randomly occurring external events. Thinking about something that will cause your product to fail regardless of how old or young it is. That is analogous to environmental causes of failure. So let's just say a vehicle is all the cars being driven across the world. The only time they fail is when people crash them. So human accident or human error is behind those vehicles crashing. You would expect to see a constant hazard rate for those scenarios, because it doesn't, if it's down to human error, doesn't matter how old or young the car is, it's equally likely to be wrapped around a tree by a human making an error. So you do see those sorts of failure patterns for human errors, dropping the coffee mugs, wrapping your car around trees. But unless every single one of your failures is driven by those sorts of stresses, you're not going to have those data points like those red ones on the left, right, those red ones right there, come through your Weibull plot. All right, so hopefully you're with me so far, and hopefully you can see I'm staying true to my pledge to minimize the number of equations I'm talking about. All right, so why is my computer deciding to have kittens right now? So what we're going to talk about right now is using this in practice. This thing right here is a vehicle. That's not particularly ground shattering, but this is a vehicle which we might be interested in improving its reliability. And when I say a vehicle, it's a very special type of vehicle. It's clearly not something you see driving around highways. It's a mining truck, a really big mining truck. It's got a 400-ton payload, which is just mind-boggling. It's so hard to wrap your head around the amount of mass this thing can carry. And they'll often be used non-stop. Like you'll often have them used 3 shifts a day. They might come in for refueling every 2 weeks or so. There might be some preventive maintenance, but apart from that, they don't stop. And they cost maybe $5 to $6 million US. Now, let's just say we want this thing to be really reliable. If this thing's unreliable, then we don't make money for our mining operation. Now, the heart and soul of this mining truck is its engine. And when we say an engine, just like the truck, it is a really big engine. This really big engine has 20 cylinders. It's about 700 to 800,000 US dollars as well. And of course, this is one of the things that contributes to real world failures for our mining truck. So let's just say we are focusing on the reliability of this really big engine. And let's also say that we have got some data points for the failure of this engine. Let's look at what those data points are. And these are real. These are real data points. And remember, these data points that come from the different factors influencing how our thing's failing, variation in the way our people use our truck, the different drivers, different terrains, you name it. And see, here are our data points, a bunch of data points that we have collected through Patch's CMMS. Now, when we plot these data points on a basic cumulative distribution function chart like this, you can see the data points create a relatively smooth line, not a straight line, but a smooth line. And we have 28 times to failure plus 50 right censored data points, which means that we have times, for example, when we're inspecting these things or doing maintenance, where at that particular point in time when we're doing this analysis, some engines simply haven't failed yet. So we have 50 engines that haven't failed and 20 engines that have. And so here are the 28 data points and 50 right center data points for our monstrous engine. Now let's convert these to a Weibull plot. And there is a Weibull plot for our engine. Now, this is a real world chart. This is what you often expect, this sort of line emanating. Now, some of you might be saying, hey, I thought you said you always get these straight lines. And that clearly isn't straight. If you're thinking of that, fair enough, I take your point. But what I actually said is that Weibull plots will give you straight lines for specific failure mechanisms, not specific components or specific engines, specific failure mechanisms like fatigue, wear, or corrosion. And as we know, big engines have different failure mechanisms that cause them to fail. They themselves have hundreds of components. And so when you see a curvy line like this, what it tells us is there's almost certainly multiple failure mechanisms at play. So let's have a look at what's going on with this Weibull plot. In fact, we can break this Weibull plot down into different components. Now we can use different markers to characterize or visualize the different components of that engine failing. And so our engine fails when a certain components fail. And here we have, with a red triangle, a yellow cross, and a green square, the failure data points for the 3 most failure-prone components of our engine. Now let's focus on their red triangles first. Let's get rid of everything else besides these red triangles, which are the times to failure for the scavenge pump. Now, the scavenge pump, amongst other things, gets rid of or pumps fluid and things like that. And if we get rid of those other data points and just plot these scavenge pump data points on a Weibull plot, well, we have a very straight line, and the data and the software we use to create this very straight line has also given us a confidence interval. This region here, this red region, shows us where the computer thinks it's 95% likely that the true line of best fit lies. And you can see that this confidence interval is very narrow, which is great. That means our software that gave us this confidence interval is very confident that that is the typical time to failure shape for our scavenge pump. And you can see that it's very, very steep. Now, what does that mean? Anyone want to hazard a guess? I'll answer that question in a tick, Fred. Wear out, fantastic. So, Kwang, you're close when you say high hazard rate. That doesn't tell us if it's high or increasing or high and decreasing. We can't initially tell that straight away, but I think you're talking about a hazard rate which is increasing. If that's the case, well done. You got it. Wear out. Hazard rate is increasing. Things that get older, the scavenge pump as it gets older is less likely to survive the next day. So that means our thing is wearing out. Now, just for those statistical boffins out there, which includes Fred, when plotting only the red triangles, all the other points, failure points or otherwise, become censored, because this is just, when we're focusing on just our scavenge pump, it doesn't matter if or when anything else fails. If the engine failed due to something else failing besides the scavenge pump, it means our scavenge pump was still working at that time to failure, then that becomes a censored point for the scavenge pump. And so we have 6 data points for our scavenge pump. And with all those censored data points, we still have a really tight 95% confidence interval. Now, if we use our Weibull plot, and for those of you who might be looking at those weird spider web of things at the top left-hand corner, when you do these things manually, that little spider web up there helps you estimate the gradient. And in this case, the gradient's incredibly high, not close to 9. So clearly, because beta is greater than 1, our thing is wearing out. So what can we do to address our engine failure given this scenario? Anyone? What can we do? Redesign. Oh, let's get back there. Redesign. What that means is that, oh, my computer is having kittens again. It loves moving on the next one. Let me get myself back here for a tick. What it means is that if the thing is failing, let's just, for lack of a better term, normally, which it is. Come on. So when things are wearing out. Oh, I've gone now. When things are wearing out, we're having technical issues at my end. What that usually means is that our thing is failing the way it's sort of supposed to fail. But that means now that we have to essentially redesign it, because it's doing something, it's failing exactly the same way, or that sort of the right way, for lack of a better term. It's failing in a very normal way. And so the pump itself might be wrong. It might be the wrong pump to use that for that engine. And as if anyone who knows these engines, the scavenge pump is a tiny part of that engine. It's very easily replaceable, very easy to upgrade. And you can see that in our Weibull plot, essentially, that uptick at the end where our engine starts to wear out overall is almost entirely caused by the scavenge pump. So you could extend the servicing interval by simply replacing the scavenge pump, which would be almost free, because they're so inexpensive compared to the overall cost of the engine itself. And you might have to service twice as infrequently or half as often. Now let's look at the next sort of dominant component which is causing failures. And that was the one which was represented with those green squares, and that was caused by the bottom end in the crankshaft, near the crankshaft in the engine itself. So here are those green squares representing the times to failure of those bottom end components. Now, if we look at the Weibull plot for that bottom end, you can see that there's quite a few green square data points. And when our software does its thing, creates the line of best fit and the confidence region, you can sort of see that it's pretty comfortable about the slope. Now, regarding this slope here, it turns out that the slope is approximately equal to, using that little spider web in the top left-hand corner up there, the slope is equal to about 1. Now, for those who've done Weibull plotting frequently, you're never going to get a perfect correlation between the slope of a line and what the actual failure process is. In this case, the slope is 1.11. So as a rule, I'd be strongly suspecting that this has a constant hazard rate, or beta is the true beta, for lack of a better term, is 1. It's quite rare to see beta parameters which are this close to 1 without them actually being 1. And so if that's the case, what does that mean? What does that mean for what we would expect to what we could do to improve the reliability of our truck? What could we do? What would we recommend? Investigate, do RCA, yep. Check for how the operator uses it. Nice. Improve robustness and better process control. Yeah. Supply controls and mitigate manufacturing defects. Not quite, because if the shape parameter is equal to 1, that means it's not wearing in. So I wouldn't look at manufacturing defects. Maybe add redundancy. Not easy for bottom ends. But it turns out that when they did the RCA for this particular component failing, the bottom end's failing, it was failing because there was an issue with the installation. And the installation might that people might think that that's clearly a manufacturing defect, but in this case, there was it left a certain amount of contamination in the lubricant. Why is that a problem? Well, the reason it's a problem is because every now and then that particular contaminant would get in the bottom end and cause it to fail immediately. And so it didn't matter how old or young that bottom end was, it would fail immediately when that contaminant got into it. And so the RCA showed that suggested that this thing should be failing due to should be failing with a constant hazard rate pattern, which is essentially exactly what it saw. So let's move on to the next one. And the next one was had these the time to failure data points were modeled with these yellow crosses. This is the valve train. Now the valve train, when we look at the Weibull plot for this one, you can see straight away that the slope is now very, very shallow. So what does that mean? Shallow slope? Anyone? We're in infant mortality failure. Yes. Sorry for those with the screen that's frozen. I'm not sure what's going on there. Zoom's not liking me this morning. Infant failure, infant mortality, we're in. And you better believe that when they did the RCA for it, they found that, now it looks like my video is frozen at mine, they certainly found, 100% found, that unfortunately there was a supplier issue with the valve train. And so the root cause analysis for the valve train was all about trying to improve those supply issues. And so what that meant was they were now able to use this Weibull plotting approach to look at how to use these things and how to address these failures. And when they did, they were able to target very specifically making data-driven decisions. That's a big buzzword these days. really useful ideas for making sure their thing would not fail again. Essentially, this Weibull plot here provided a huge amount of information without any need for equations or anything like that, even though we did have parameters and things like that. Fortunately, we don't have to use equations all the time to get meaningful data outputs or meaningful information to improve the reliability of your products. Now let's talk about Weibull plotting software for the last little bit of today. Now, there's a good chance that you're going to see me frozen on the left-hand side on the screen. There we go. So just imagine that person on the screen just talking as we go. So for those people who are stuck with me so far, now Weibull plotting software. Could I just ask, do a little bit of a survey, and people who answer yes, just give me a thumbs up and I'll be able to count these thumbs up in the participants tab on my screen. So Weibull plotting software. Who has heard of it? Who has heard of Weibull plotting software? So we have one. So not a lot. Okay. So I've got a bunch of yeses and I can't find the thumb. All right, no worries. So I have to do it old school. I'm trying to count furiously as the yeses and the thumbs up comes through the chat. So I'm going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. All right, cool. 16, oh, 17. Any more? All right. For those who have heard of it, who has used it? So I'll reset my counter. Who has used Weibull plotting software? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 13. So 17 people have heard of it. 13 have used it. All right, cool. Now, next question. Those who have used it, 17, 13. For those who have used it, would you change if there was another platform that was easier to use? And the answer, that's a no. So not a lot of people would change. Oh, got 1. 1.5. 1 3/4. Very weak. That's cool. All right. So we're very strongly committed to our extant Weibull plotting software. So 17, 14, I'm going to maybe add those up to 2 or 3. Next question is, would you change if there was another platform that gave you more accurate confidence bounds and parameter estimates? Oh, I reckon there's going to be a ton of no's. Oh, yes. Oh. So up to 3, couple of maybes, 4. I'm going to count those, all those maybes as a 4-ish. Probably 4.75. Okay, so maybe you score that one as a 5 or a 6. So team, unfortunately, for whatever reason, the screen has frozen my video. So you're gonna have to deal with me looking like this for the rest of today's conversation. Apologies for that. But just imagine me at the other end of this video, just as animated as I usually am. Shashir, no worries. It's another conversation to have. And on that note, you can please feel free to check out the other webinar called Confidence in our Conclusions, which helps explain where those confidence bounds come from. So we're going to wrap up today's conversation with that little survey, which is mainly done for my selfish curiosity more than anything else. But for those who have stuck with me through the end, thank you very much for listening to my nonsense regarding Weibull plotting. I'm going to open it up for any questions and answers. I'm going to go through the chat and answer questions that were asked. And I know that, for example, one of the questions was, if we don't have info on devices in the field which are still operational, what options do I have to determine censored devices? That's a very good question. Now, it's a very statistical question because when it comes to Weibull plotting, censored data is still data. You have to include it. So let's just say you might have 30 or 40 devices in the field and you might have 10 failure data points. I'm not sure what the example, the scenario is you're talking about. But when we do Weibull plotting, we incorporate those censored data points in a very methodical, clear way. And we did just that for the engine for our mining truck, if you might recall. Remember, our engine had 50 censored data points, which means 50 engines were still working. 28 had times to failure, and those 28 combined with the censored data points created that Weibull plot. Now, although you can't see those censored data points, they certainly impact the Weibull plot itself. And I might give an example with the very first one we had when we started examining the scavenge pump. Now you can see here is a Weibull plot with the 28 data points for our engine. You can see the red triangles at the top right-hand corner, scavenge pump failures. Now, essentially, if we disregard all the other engine failures when the scavenge pump was working, they become censored data points for our scavenge pump. And that means the Weibull plot, watch the red triangles, they don't stay in the same spot anymore. They move to different points on our Weibull plot. And that's because there is a huge change in the censored data points now that our item of focus is the scavenge pump. So we have a total of 78 data points. Remember, 28 engine failures. So only 50 censored data points, but for our scavenge pump, where we have 6 data points, that means we have 6 times to failure and 72 censored data points to create this Weibull plot. Does that answer your question? Is that Yeshwanth? Did I get your name correct? No worries. Vasu asks, regarding the y-axis of the Weibull plot, how do you account for new units entering operation continuously to calculate the percentage of units still alive? Now, that's a good question. Now, the percentage of units that are still alive for our Weibull plot are based on the age of the component or the system or the product. It's not a snapshot in time. So this will tell you the probability of failure, or sorry, Weibull plotting can help you determine the probability of failure for a component based on its age. Now, what that doesn't mean is that if you have new units constantly being inserted into circulation, that you won't be able to from the total number of units being used, you won't be able to deduce the expected number of things that are still working unless you have the age of each one of those things. So you can't do that, if that answers your question, Vasu. You need to have the age. You want a webinar on warranty analysis. All right, Fred, we'll add that to the list. Thank you, David. Yes, so censored data points, suspensions or suspends, it's another term for data that is essentially telling us that that product's still working at that point in time. Thank you, Brad. Did I miss any questions? I don't think I did. Apart from questions about the webinar being recorded and available thereafter, which I think Fred answered. Now, I did have some technical issues, which is my want, apparently, for my webinars these days at my end. Marcel, the reason why I wanted to ask you about the Weibull plotting software is because, at least in my some of the things I do, the accuracy and the validity of Weibull plotting software outputs is kind of a big deal, especially when it comes to the confidence bounds. Most Weibull plotting software uses at least 6 assumptions to create those 90% confidence intervals. Again, I have a webinar on that through Ascendo, which sort of talks to that. And so it was just one of those things, because I'm constantly looking at what I need to do and in my life and in my professional life, and what I should be recommending and what I should be investing my efforts into. And it's always good to know if there is an appetite for moving towards Weibull plotting software where those confidence bounds are spot on, not just rough approximations using 6 different assumptions, which can be spectacularly wrong if you have, in particular, a small number of data points. Shashir, how do we use a log normal model instead of a Weibull model? Can the slopes on the log normal plot be interpreted in a manner similar to their interpretation on a Weibull plot? And the answer is no. Good question, because this is a Weibull plot, this plotting paper you see on the screen right now. It's a plot that makes Weibull data points create straight lines. Lots of different probability distributions have the same capability. They have the ability for us to create plotting paper just like this, but with different scales, with different squishy bits here and there. And essentially what happens is if you have data points described by a log normal distribution, those data points will create a straight line on the log normal plotting paper. The answer is no, because log normal distributions by definition model things that wear out. So you will only ever get data points that create straight lines on a log normal plotting paper if they're modeled by the log normal distribution, which means by definition, they are all wearing out. If you have something which is wearing in, it will create a violently curved line on a log normal plotting paper, which means you can't deduce too much from it, apart from the fact the log normal distribution doesn't do a good job of modeling it. The Weibull distribution can model things that wear in, wear out, and anything in between. The log normal distribution can't. Does that answer your question? No worries. Any more questions? Comment, the easiest is the world confidence interval, more compute intensive. CI is based on simulation. Yeah, Markov chain, Monte Carlo simulation. But that's theoretically the only way you can get the correct confidence bounds. There is no analytical solution or theoretical solution to the exact confidence bounds for a Weibull plot. Any more? All right, Fred, I think we're less than half of our initial team still online, so yes, it's time for us to wrap things up.